Welcome back to the study of ionization energy. We already have a fair idea of how an atom looks like. In fact, we have already seen in the study of Bohr's model that the electron keeps moving around the nucleus in different shells. If it is moving closer to the nucleus, it has a lesser energy, and if it takes certain energy, it will jump to a higher shell and starts moving in the higher shell. However, it cannot stay in the higher shell forever. It comes back to the lower shell by releasing certain energy. We were very curious to find out how exactly this energy is taken in and taken out of the electron, and we wanted to study more about how exactly this process happens. And scientists figured a way to find out that electrons do absorb energy, and they found out by using something called as a spectroscope. So what was basically done was a gas was taken in a chamber and it was given high energy in the form of heat or passing electric current through it, and obviously the electrons could take up that energy and they could jump to the higher energy levels. And they were not in the higher energy shells forever. They came back to the lower energy level, and in the process of doing so, they released some energy. They emitted the radiation. Now this emitted radiation was recorded and gave rise to something called as emission spectrum. What is this spectra? It is not a continuous spectra as we get it from the sun, but it was more of certain lines present here and there in the spectrum, and hence we also call the spectrum as a line emission spectrum. Now this line emission spectrum is a very important spectrum because this acts like a fingerprint to the element. The lines that we get is very specific for a particular element. Also, it proves that the energy is always quantized. It comes in the form of certain packets which we call as the photons. So once we got to know that every shell has got very specific energy and this energy has to be given or is released for the electron to shuffle between these shells, we were interested to find out how exactly elements can be ionized. So what exactly do we mean by ionized? Now we know that if I give energy to an electron, it jumps from a lower shell to a higher shell. Just imagine I give so much energy for the electron that it jumps not to any of the shells, but I take it to an infinite distance. Now the distance is so much that there is no attractive force from the nucleus to the electron. We always believe that nucleus being positively charged, electron being negatively charged, there is always some kind of force of attraction between them. Now, if I move them to the infinite distance and there is no attractive force between them, that is when the atom is said to be ionized, because the atom has a positive charge. Right? So basically, the energy that I need to supply to the electron to completely remove an electron from an atom of an element is what I call as ionization energy. So just imagine we have an element here. So this is carbon having 6 electrons. If I take out one electron from this, let me say, to the distance, which is almost infinite distance, I would say, where the nucleus has no influence over this electron, then this atom is actually having a positive charge, which I would call as a cation. The energy that is required is what I call as ionization energy. Now comes one very important aspect. Now suppose I take an electron, let me say, to an infinite distance here. Now what is the energy of this electron? Is it energy of an electron present in this shell, or is it energy of the electron present in the inner shell, or what exactly it is? Now we have seen that the energy which is present here, which is at an infinite distance from the nucleus, is always the same regardless from where in the atom it has come from, whether it is in the first shell, from the second shell, third shell, or so on. It does not matter as long as it is at an infinite distance. You see that it possesses certain energy. Right? Now this energy is something which is very important, because that is how we are going to define our ionization energy. Now ionization energy is nothing but the energy of the electron when removed minus energy of electron when in the orbital. So if the electron I am taking out is already in this higher shell, that requires a lesser energy for me to remove, whereas if I am taking an electron from the lower shell, I need to give higher energy for this electron to be taken out to an infinite distance. So that is all about what exactly ionization energy is. Now you might be wondering, why exactly do I need to know about this ionization energy? Now ionization energy is a very important indicator of reactivity. We know very well that the reactivity involves formation of molecules, compounds, and so on, for which there is always either giving away the electron or sharing the electron. That is measured by one value, which is our ionization energy. This is also an indicator of the strength of the chemical bonds, and therefore it is very important for us to know about ionization energy in chemistry. Now that we know what is ionization energy, let us learn about something called as the first and second ionization energy. Now what is this first and second ionization energy? Imagine that we have an atom which has many protons and therefore many electrons. Now how many electrons can I take out, at least hypothetically, from this atom? It would be as many number of electrons that it has. The first electron that I would take out from this atom requires energy, and this energy would be the first ionization energy. Always we see that to just take out one electron from an atom, it is always slightly lesser energy, and first ionization energy value is always lesser. But is it possible for me to take out another electron as well? Yes, I can always take out another electron too from the atom, and if I take out a second electron, that becomes a second ionization energy. The energy required to take out the second from this atom from which I have already taken out one is what we call the second ionization energy. Always you see that the second ionization energy is slightly higher than the first ionization energy. Many times you also see that there is third ionization energy, fourth ionization energy, fifth ionization energy, and so on. And every electron I take out, the successive electron that I am taking out requires higher energy. Now why do you think that is so? That is because as I keep on taking out the electrons, you see that the nuclear charge is still the same. It's the constant here because I'm not taking out the protons, right? So the protons are having a higher affinity to all the electrons that are present in an atom, and therefore since the nuclear charge remains constant, it has a higher attraction towards all the electrons that are already there. Hence the second ionization energy value is higher than the first. Third ionization energy is higher than the first and the second, and so on. Now this is a graph where the log of ionization energy is plotted against the number of electrons that can be taken out in an atom of sodium. So we know that sodium has 11 electrons. So hypothetically, it is very, very difficult for us to take out all the 11 electrons from sodium atom. The energy required to take them out is calculated, and yes, certain experiments are also done to take out all the 11 electrons from the sodium atom. Now you can see that to take out the first electron from the sodium atom, the energy required is less. However, if you notice, these are showing a slightly higher value than the first ionization energy. However, you see that the values are not very, very different, and then you have a sudden jump in the ionization energy for the last two electrons. Carefully looking at it, you can see that the first ionization energy involves the removal of electron in the outermost orbit here, which is n is equal to 3. Now, removal of the second shell electrons, the next 8 of them, would be from the second shell here, and you can see that they are fairly higher than the third shell. And to take out the lower most shell electrons, you see that we need to give a higher energy. So this clearly shows that if they are in the lower shell, higher energies have to be given for the electrons to come out of the atom, and if it is at the farther distance from the nucleus, we need to give a lesser amount of energy. Now this is one more graph which is showing us the first ionization energies of 12 elements, not talking about the second, third, fourth ionization energies. It's only the first ionization energies, and we are talking about the first 12 elements here. Talking about the first 12 elements, to take out one electron from hydrogen, I need to give some energy somewhere between 1230 kilojoule per mole. That would be the first ionization energy here. However, if you talk about the helium, you see that the helium ionization energy is higher. There is a sharp increase for the ionization energies of hydrogen and helium. Element from the periodic table, lithium, you see it is very easy because it has a very low ionization energy, but again beryllium has slightly higher. Boron, carbon, nitrogen, you can see that all the three of them, boron being slightly lesser, then it slightly increases. Again you see that oxygen is slightly lesser than nitrogen, again it increases, and then falls sharply for sodium, and again for magnesium you see that it increases. If you look at this very carefully, you see that there is some relation between the shells and the subshells too. You can see that as I need to take out the electrons from the p orbital here, boron, carbon and nitrogen, you can see that there is a linear relationship. This is also kind of quite stable because the subshells are half filled. But again, if you talk about oxygen, oxygen has a lesser ionization energy because I want you to think about the electron configuration of oxygen. You will have one of the p orbital which is doubly filled, and therefore taking out an electron from that would be easier, and then fluorine, and then we have the neon, which is the maximum because all the shells, S shell and the P shell, both of them are completely filled. So there is a strong relationship between the shells, the subshells in which our electron is, to the ionization energies. Let us talk about one very interesting aspect which is called as the shielding effect and the nuclear energy. Consider an atom here. The atom that is shown to you here is helium. Now we know very well helium has 2 electrons, right? What about hydrogen? Hydrogen has 1 electron. Let us talk about something called as the shielding effect and nuclear energy. Imagine that I have only 1 electron revolving around this nucleus. There is only 1 proton here, and there is a force of attraction between the proton and the electron. You agree with this, right? So there is a force of attraction between the proton and the electron, and you see that the electron is kind of revolving around the nucleus. And to take out this electron, I need some energy, which is the ionization energy of hydrogen. Now, suppose there is one more electron, as we see in helium. You always see a repulsion between the 2 electrons present in the shell, right? And don't you think in this particular case, it should be very easy for us to take out 1 electron? it has to be, right? But as you notice in our previous diagram, you see that the helium has highest ionization energy, and therefore our theory might not be true in that case. So what exactly is happening here? Though there is a repulsion between these two electrons, you should never forget that there is also addition of one more proton in the case of helium, and therefore the effective nuclear charge, right, the effective nuclear charge is increased. Now, because the net effective nuclear charge is more, you can see that even though there are these two electrons experience some kind of repulsion, there is also a force of attraction of the protons of helium atom towards both the electrons equally, so that it is very difficult to take out an electron from this first shell. Hence, the helium atom has higher ionization energies. Let's take a complex atom having many electrons as our example. You see that the electrons are present in the inner shells, they are present in the outer shells, and you also see that for every electron that is added in this atom, there is also an increase in the number of protons in the nucleus. Now, as you increase the number of protons in the nucleus, there is increase in the nuclear charge. Now, this increase in nuclear charge can hold as many electrons as possible, right? But you notice that though the nuclear charge is increased, the electrons which are inside would experience a much higher nuclear charge than the outermost electrons here. Okay. Now, why is that? That is because the innermost electrons here, are kind of shielding the charge to move to the higher shells. Now, this is what we call as the shielding effect. Many times what you see in helium, where there is repulsion of two electrons but they both stay together experiencing the same nuclear charge, is also called as a screening effect or the shielding effect. However, that is predominantly seen in all the larger atoms, where the inner electrons are kind of shielding the charge, nuclear charge, to the outermost shells. Now, that is what we call as the shielding effect. You can take out electrons from the outermost shells as we increase the atomic number of the elements, and they are quite unstable too. Now, with all this, let us try to figure out how to find the energy of an electron. All this time we were thinking that the energy of an electron comes from the shell in which the electron exists, but it is not just the shell. We realize that it can be the orbital in which the electron exists also. S has lesser energy than P, P has lesser energy than D, D has lesser energy than F, and so on. But it is not just the shell and the orbital, but it is also the nuclear charge of the atom, with what force the nucleus is pulling the electron towards the nucleus. That is also deciding factor for the energy of an electron. And it's not just that. The number of other electrons that are present in an atom also plays a very important role, because they give rise to some kind of repulsion, electron-electron repulsion, or there can be a shielding or a screening that an electron can experience from all the other electrons that's present in an atom. So with all this, you see that the energy of an electron is not just determined by one factor. In fact, it is because of this reason that we say the energy of an electron at an infinite position will always be the same, regardless from where in the atom the electron has come. So with this, let us end our topic on ionization energy. See you soon.